This new module that we're starting is all about buffers, which are a special type of solution which involves acids and bases, and they will always involve a weak acid and its conjugate base, or a weak base, and its conjugate acid. And we see these buffer solutions in the ocean, we see them in lakes, we also see them in the bloodstream of all kinds of different animals. So let's begin. Buffer solutions are often used in biology, and they're often used in chemistry. So for example, if we wanted to grow an organism that we'd say collected from, say, a hydrothermal vent system or from a lake, we would want to grow that in some type of media. And so again, if we were trying to grow some type of bacteria, we would want to grow this in some type of media. And in order to do that, it has to have the correct pH. And so to produce a solution with the correct pH, we have to have the ability to do that. And this is what's called a buffer solution. So for example, if we look at, say, extremophiles, which are organisms that grow in hydrothermal hot springs in this case Yellowstone National Park, or in Tanzania, there are organisms that live above 80 degrees centigrade. These are often called extremophiles. And if we wanted to grow these, we would have to grow them in some type of medium that is similar to what they actually grow in the normal situation. And so, for example, here this would have a pH of 3, highly acidic. And so we would be able to make a solution that could produce that. And again, you know, if you were growing, say, cancer cells to test for drugs, you would want to have that pH constant around about 7, similar to what you would expect to see in the human body. And so to make these a buffer solution, the definition of a buffer solution is a buffer solution resists a change in pH when small amounts of strong acid or strong base are added. So in other words, if you add a small amount of acid or a small amount of base, the pH changes a very small amount. Normally, if you add acid and base to any type of solution, say an aqueous solution, the pH is going to skyrocket up or down when you add acid or when you add base. And a buffer solution has the ability to resist that change. But of course there are limits. Like everything in chemistry, there are limits. So if you add too much acid or you add too much base, then the buffer system is not going to work anymore. And so buffer solutions, such as human blood, are great so that when we eat something like highly acidic, like tomatoes or orange juice, our blood in our body doesn't suddenly change its pH massively because we've consumed something acidic. It has the ability to resist a change in pH. And so when we talk about buffer solutions are a solution of a weak acid, not a strong acid, a weak acid, and its conjugate base. And so just like we've been writing similarly, or recently we've always been writing the fact that if you take an acid, this is acetic acid, and you add water, it's a reversible reaction, and you produce hydronium ion plus, in this case, acetate ion, which is the conjugate base. Here's the acid, here's the conjugate base, just differs by 1 proton, and this is the conjugate base. So if we want to make a buffer, an acidic buffer, we would have a solution of a weak acid and some of this conjugate base. So we need a source of this conjugate base. And so the source of this conjugate base, which is acetate, we need something that's going to give us acetate. And so the source of a conjugate base, if we want acetate, we would add something that produces acetate in water. So for example, sodium acetate, the great source of this. If we take sodium acetate and we put it in water, it dissolves and it dissociates to produce acetate ions and sodium ions. So here we have the source of acetate ions. So if we wanted to make a buffer solution of a weak acid, we would take acetic acid, and then we would need some of its conjugate base, and its conjugate base is acetate. And in order to get that, we would add some sodium acetate. And you might say, well, what happens to this sodium over here? Well, this sodium dissolves in water, it's in the solution, but it's not involved in the reaction. And so if you wanted to make a basic buffer, so a basic buffer, of course, having a higher pH, you would take a weak base, such as ammonia, and its conjugate acid. So here's ammonia, we add it to water, we produce OH minus, hydroxide ion, because of course it's a base, and here NH4 plus is a conjugate acid of this base. Again, differs by 1 proton. And so to make this solution, we would need a solution of ammonia and its conjugate acid, which is ammonium ion. So we would need to put something in the solution that produces NH4 plus. So in the case of ammonium chloride would be a great example, because ammonium chloride, you put it in water, it dissociates, produces NH4 plus ammonium ion, which is exactly what we want up here. There we go. And then it also produces chloride ion. What happens to this chloride ion? Well, the chloride ion is soluble in water, so it's in the solution, but it's not involved in the reaction. And so we can make these buffer solutions out of a weak acid or a weak base. And now let's just have a look at how this actually works. So if we take this acidic system, so here's acetic acid, here's acetate, the conjugate base, here's hydronium ion, because this is an acid reaction. And if we think about this, if we have a buffer solution where we have equimolar, meaning we have the same number of moles of acid and conjugate base. So here it's a 1-to-1 relationship. And what happens when you add some acid? So if you were going to add some acid, remember by Le Chatelier's principle, if you added a product, so here if we add some extra acid, H3O plus, what's this equilibrium going to do to react to this or to counter this disturbance? Well, it's going to go to the left, because it's going to try to utilize this H3O plus. And so if we add H3O plus hydronium ion or acid, the equilibrium shifts to the left. So it shifts to the left. And when it shifts to the left, of course, there's going to be a little bit more acid produced, and there's going to be a little less acetate. So this ratio is going to be slightly different than it was initially, but it's only going to change a small amount because of this equilibrium reaction, that it's able to move to the left. And so the pH is going to change, but it's only going to change by a small amount. And so you might say, well, what happens if I add a little bit of hydroxide ion? Well, if you add hydroxide ion, as you add hydroxide ion, it's going to react with the acid, and when it reacts with the acid, so you're effectively on the reactant side, when you add hydroxide, the acid is going to react with it, it's going to produce H2O and some acetate. Oh look, there's the acetate. So the reaction is shifting to the right. So when you add OH minus, in this particular case, the equilibrium shifts to the right. And so when it shifts to the right, you're going to have slightly less acid, slightly more conjugate base. So the ratio is going to be somewhat different to what it was initially, but because this is an equilibrium reaction, because it's able to absorb some of that acid or some of that base, the pH is going to change, is going to only change a small amount. So how about a basic buffer? So a basic buffer would require a weak base and the conjugate acid of that weak base. So how do we determine what that conjugate acid would be? What chemical or substance could we add? Well, if we draw out this relatively standard reaction that we've talked about, here's a weak base, and we add it to water, it's in equilibrium with its conjugate acid, NH4 plus, because see there's only an H plus or proton difference between these, and of course it's producing hydroxide ion because of course it's a base. And if you look at this, we realize this is the weak base and this is the conjugate acid, so we need a source of NH4 plus, and so we can get that from anything that's going to produce NH4 plus or ammonium ion in solution. So ammonium chloride great example. Ammonium chloride, you put it in water, it produces ammonium ion and chloride ions. Here's the ammonium ion, that is a source of this conjugate acid. So to make this solution, we would take ammonia and we would take ammonium chloride, we would put them together and we would make this buffer solution. And so what would happen if we added a little base to this reaction? So if we add some base, and a strong base, sodium hydroxide, when you put it in water, dissociates to produce sodium ions and hydroxide ions. And so if you added a few milliliters of base, you would be adding hydroxide ion. And over here, so on the product side, Le Chatelier's principle would say if you add some product to a reaction, the equilibrium is going to react to this. And because you're adding it on the product side, the equilibrium is going to shift to the left. And it'll shift to the left to be able to effectively absorb or consume that hydroxide ion. And so the equilibrium will shift to the left. Conversely, if you added a little acid, so here for example hydrochloric acid, a strong acid, we react it with water, it produces hydronium ion and chloride ion. And so this hydronium ion, what's this hydronium ion going to do? Well, it's going to act as an acid, and so it's going to react with this base over here. So effectively, on the left hand side of the equation here, this ammonia is going to react with this newly added H3O plus, and the reaction is going to move to the right and it's going to produce NH4 plus, which is in fact the conjugate acid plus some water. And it's great because the solution is all in water. So if you add a small amount of acid, this reaction is going to shift to the right. And if you add a small amount, it's able to absorb or react to this without much of a change in pH. And so where do we see this? Well, here as an example, if you grow tomatoes, their soil pH needs to be around 6 to 6.8. And so if you were going to grow them at home or in a greenhouse, you would typically be using some type of buffering system to try and keep that pH very close to 6.0 or 6.8. Outside those ranges, the buffering capacity inside the tomato is not really going to be very happy. And here, for example, if you look at the marbled salamander, they looked at soil preferences in Huntington, Pennsylvania, and they actually saw that these salamanders have a pH of 5.1 on average, and so soils themselves have buffering capacity, and so they keep their pH relatively close together. So if there's some acidic rain or acidic deposition, many of these soils are able to buffer that. And so certain organisms like a buffering capacity so that their pH is pretty constant. And of course, if you like to have your own aquarium, you can go to the store and you can buy something called Instant Ocean, which comes in a packet, and you mix it with some water and you chuck it in your tank, and it effectively has the same pH, about 8.1 of the ocean, and it's of course called a sea buffer because it's a buffer so that let's just say some fish do some peeing in there, the pH is not going to change markedly in the tank, because this is going to be a buffering system. And it says indeed increases and maintains the pH and alkalinity of this system, so it's acting as a buffer. And so let's just briefly look at what buffering capacity looks like. If you look at a plot which has the amount of sodium hydroxide added, so this is the base, and what we have here is we have acetic acid, and so acetic acid is we've made an acetic acid buffer with some acetate, the conjugate base here, and what happens is as we start to add more and more sodium hydroxide, we can monitor the pH. And as you add more sodium hydroxide, more base, you'll see that there's a very small amount of change in the pH. A very small amount of change in the pH as you're adding considerable amounts of sodium hydroxide of base. And so this pH here, this is the buffering capacity. You keep adding sodium hydroxide, but the pH doesn't change much. Then at one point, just around about here, the buffering capacity is exhausted. And when the buffering capacity is exhausted, all you have to do is to add another, in this case, 2 milliliters of sodium hydroxide, and the pH just skyrockets and becomes extremely alkaline. And so this is the buffering capacity of this particular buffer, this acetic acid buffer. And so it's able to keep the pH within 4.8 and 6 over a considerable range. But after that, if you add any more, it will skyrocket. And so this is a hypothetical situation. If you look at the ocean has a rough pH, or it used to anyway, of about pH of 8. And if you keep adding CO2 to the atmosphere, CO2 then goes into the water, it produces CO2 aqueous, that produces carbonic acid. And so when you add carbonic acid in the ocean, the pH stays remarkably consistent, maybe decreasing just a little bit, but this is the buffering capacity of the ocean. So if we keep adding CO2, the buffering capacity keeps the ocean at a pretty constant pH. However, at some point around about here, whatever that point is, if we add any more CO2, it's what's called the tipping point, and at that point the pH is just going to start to plummet in the ocean. And so we are roughly in this area over here where the buffering capacity is coming to the end, because the pH of the ocean has slowly started to decrease, and at some point it's going to get to this tipping point, which is going to be a scary time, where the pH is going to plummet of the ocean. And we're still a considerable way off, and we can still do something about it. So, not to be the harbinger of doom. And of course, this was an oversimplification of the ocean system. So, keep slowing down the amount of CO2 you're putting into the atmosphere, and this won't happen.